me this opportunity to present our work. And so today I will talk about our recent work regarding integer partitions. We proved four conjectures of Berkovich and Uncu regarding some inequalities consisting of sets consisting of partitions. And so we recall by so we begin by recalling some basics of integer partitions. An integer partition of n is a way of writing n as a sum of positive integers such that the order does not matter. For example, 4 can be written in the following ways. So there are 5 partitions of 4. And when we say that the order does not matter, we mean that 3 plus 1 is considered the same as 1 plus 3. So we don't count them twice separately. And we also write the norm of a partition pi equals n to indicate that pi is a partition of n. And so in this talk, we will be using a somewhat non-standard notation for integer partitions. So we write pi as 1 to the power f1, 2 to the power f2, and so on. So where fi is the number of times a part I occurs in pi, so let's say 1 occurs f1 times, then we write it as 1 to the power f1, and similarly 2 occurs f2 times, so we write 2 to the power f2. So this is also known as the frequency of I. And so thus, suppose we have this partition of 13, so 4, 4, 2, 2, 1. So 1 occurs only once, so we write it as 1 to the power 1, and 2 occurs twice, so we write this as 2 to the power 2. Similarly, 4 to the power 2. So in this notation, it is clear that the norm of pi is given as the summation of I times fi, because like the total number is formed as the weighted sum. So like each part I occurs fi times. So the total number n is given as summation I times fi. And so we started this work when we came across a paper of Berkovich and Uncu in Annals of Combinatorics in 2019. So they found some surprising inequalities for integer partitions. So they compared the size of the sets AL1 and AL2. So AL2 is the set of partitions with all parts lying between 2 and L plus 1. So where L is any natural number. And AL1 denotes the set of partitions where the smallest part is 1, all parts are less than or equal to L plus 1, and L does not appear as a part. So we say that L is impermissible. So these sets AL1 and AL2 are closely related. So they are similar because in both of these sets, all parts are less than or equal to L plus 1, but they have two key differences. So firstly, in AL1, the smallest part is 1, that is 1 occurs as a part in AL1, and 1 is not allowed to occur as a part in AL2. And the second difference is that in AL1, L does not appear as a part, whereas in AL2, L may or may not appear as a part. So with this notation, they proved that the number of partitions of n in AL1 are more than the number of partitions of n in AL2, so greater than or equal to. And so this is subject to the restriction that L is greater than or equal to 2, but this restriction doesn't mean much because for L equals 1, the set AL1 is not meaningful. So because it says smallest part is 1 and 1 does not appear as a part, so that's kind of self-contradictory. And so they had this inequality for sets of partitions. And so we skip their proof. I had this for some context, like to show how these results are proven. But if we have time, then we'll come back to this. And then
Question,
they,
Tamal, one question. So,
I-
yeah, is there any particular reason to define AL1 and AL2 in that way? So,
uh, so I mean, like this is something I would say I really don't have
okay,
an idea why they came across these definitions. So, but
okay,
they somehow noticed that there are more partitions
I
of
see.
n which are in AL1 than they are in AL2. So,
Okay,
probably it's somewhat like natural to compare these sets. So like if we see the difference between these sets, so
mm-hmm.
they all have elements less than or equal to L plus 1,
Oh,
and
yeah.
then it additionally has a 1 and no L.
Yeah, okay. These two definitions are somehow closely related. That's why they
Yes,
are interested in analyze their relation. Yeah,
exactly.
yeah,
Yes,
yeah. Thank you.
yes. And then so then they shifted the size of permissible parts by 1 unit everywhere. So like BL2 now becomes the set of partitions with all parts lying between 3 and L plus 2 instead of lying between 2 and L plus 1. And similarly, BL1 now has smallest part 2 instead of 1, and all parts are less than or equal to L plus 2. And the impermissible part also gets raised from L to L plus 1. And then they asked the same questions, and so they basically proved that this inequality is still true. So the number of partitions of n in BL1 are greater than or equal to the number of partitions of n in BL2. But this time the condition on L and N is somewhat modified. So we talk about L greater than or equal to 3 and N greater than or equal to 10. So for L equals to, it is easy to see that this is not true, because when L is 2, then B22 just consists of partitions with parts in 3 and 4. So B22 will include odd numbers because 3 is there. And B21 will consist of partitions with parts 2 and 4, so 3 cannot appear. So all the parts here are even. So BL1 can only represent numbers which are even. So for odd numbers, the first set is going to be 0, and the second set is going to be a positive number. So this is not going to be true for L equals 2. So that's why they look for L greater than or equal to 3. And so then they realized that both of these results are the initial stages of a more general conjecture. And so like instead of shifting by 1 unit, now we shift for a general of S units. So we define the set CLS2 to have all parts lying between S plus 1 and L plus S, and the set CLS1 as the smallest part S and all parts less than or equal to L plus S, and L plus S minus 1 is impermissible. So, like the sets AL1, AL2, and BL1, BL2 have been generalized here. So, AL1, AL2 is the case S equals 1 of this setting, and BL1, BL2 corresponds to the case S equals 2. And for uh, this general setting, they conjectured that there exists a bound M, and very importantly, that bound only depends on S, such that whenever n is larger than the bound, then n, the number of partitions of n in CLS1 is more than the number of partitions of n in CLS2. So, and then for the second conjecture, uh, they defined uh, so they considered another very similar set here. So they just changed the impermissible part from L plus S minus 1 to L and kept everything else same and made the exact same assertions. So basically here the impermissible part can depend on both L and S. So they made it L and removed its dependence on S. So they defined the analogous set C star LS1, so in which the impermissible part is L, and then they conjectured that the number of partitions of n in C star LS1 is greater than or equal to the number of partitions of n in CLS2 whenever n is larger than the bound M, which again only depends on S. And from these two conjectures, one naturally can think about a question like if can is it reasonable to make similar assertions if the impermissible part is independent of both L and S. So if we work with a general impermissible part instead of working with L or L plus S minus 1, so for that, we further generalize our sets. So the set ILSK uh, has again so the same conditions here, smallest part S and all parts are less than or equal to L plus S, and the impermissible part is K. Now instead of L plus S minus 1 or K, or L, now the impermissible part is K, and so it generalizes the set CLS1. So now CLS1 is ILS L plus S minus 1. So it's for K equals L plus S minus 1. And the other set, the C star LS1 in the second conjecture corresponds to the case K equals L. And then one can ask a similar question, a more general question. So when k lies between s plus 1 and l plus s, so like this is a natural condition. So since it's an impermissible part, so it has to be within the bounds, so it has to be between s plus 1 and l plus s. So the question is like, does there exist a bound M which depends only on S such that the number of partitions of n in ILSK is more than the number of partitions of n in CLS2 whenever n is larger than the bound. So, and like one can think that this is probably a bit too strong of a statement to assert that M depends only on S, even in this general impermissible part K case. So maybe one can remove this part and make a more uh, realistic question. So that is what they did for conjecture 3. But then they, instead of like talking about the sets of partitions, they considered the Q series analog of these statements. So first of all, we recall the definition of the Q-Pachammer symbol, which appears quite frequently in the theory of partitions. So it's defined as this product consisting of n terms, and the ratio of like the successive terms here is Q. So the series HLSK is defined as follows. So it's defined in terms of the Q-Pachammer symbols, and one can actually further like write out the expression. So using this definition for Q-Pachammer symbol, so we can write it out in the expanded form. So the plus one here is only to account for the empty partitions. So we don't worry much about that. And then we want to get combinatorial interpretation for this. So if we find the coefficient of q to the power n in the series HLSK, and So for that we further like split the first term into two terms. So this becomes q to the power s minus q to the power s times q to the power k, and then we have this third term. So from the elementary theory of partitions, we know that the coefficient of q to the power n in the third term is just the number of partitions of n with parts lying between s plus 1 and l plus s. So that is precisely the set consisting of partitions of n in CLS2, and the first two terms correspond to the first set. We'll see how. So like for the first term, the denominator, so 1 over the denominator means the number of partitions of n with all parts lying between s and l plus s. But when we multiply this with q to the power s, that means s should appear as a part. So together, the first term means the number of partitions of n where all parts are less than or equal to L plus S, and the smallest part is S. And then the second term has, apart from this term, it also has a q to the power k. So that means in addition to the conditions over here, so it also has k as a part. So when we subtract this, then the coefficient of q to the power n in the first term minus in the second term becomes the number of partitions with smallest part s and all parts less than or equal to L plus s, and for which k does not have for which k does not appear as a part. So that is precisely ILSK. So k is impermissible. So the impermissible part is coming from here. So like this has no condition, and this, then we subtract those for which k appear as a part. So this difference gives us that k should not appear as a part. So thus we see that the coefficient of q to the power n in HLSK is given by this difference. So like in the question before, we wanted to say that this term, this cardinality of the first set is more than the cardinality of the second set. So this means that this coefficient is positive. So if we rephrase our question analytically, so in Q series form, so it means does there exist a bound M which only depends on S, such that the coefficient of q to the power n in HLSK is positive for every n greater than or equal to m. So like we were saying before, so maybe we should remove the condition that m depends only on s. So if we do that, so then this just means that the coefficient of q to the power n in HLSK of q is positive after some bound m. And so we have a terminology for such series. So a series is said to be eventually positive if all its coefficients are positive after a given bound. So then their third conjecture is like HLSK is eventually positive. So meaning that it's positive after a given bound. So now we are relaxing the condition. We don't say that the bound depends only on S. So this conjecture is kind of weaker than the question because it uh, does not have this dependence. So the bound can depend on LS or K. However, it is stronger in the sense that uh, so the restriction on k has been removed. So here we said k is less than or equal to L plus S, so as to retain the combinatorial interpretation. But here we are just saying that the series is eventually positive for all k greater than or equal to S plus 1. And then similarly, one can also compare amongst the conjectures. So this third conjecture is stronger than the first two conjectures because it deals with the general impermissible part k instead of dealing only with those two specific values, whereas it also relaxes the condition on the bound. So now it can depend on all of L, S, and K instead of only on S. So uh, we prove uh, we prove a result that is stronger than all of these conjectures and questions. So we show that whenever k is greater than or equal to s plus 1, the coefficient is positive whenever n is greater than or equal to some bound gamma of s, where gamma of s can be written explicitly in terms of s only. So we write gamma of s as follows through these three steps. So first of all, we write p of s as this product, and then we define the quantity beta of s uh, as in terms of p of s. So, and finally, we express gamma of s in terms of p of s and beta of s. So actually, we wrote this as a sequence of three steps, because if we don't do that, then it takes a lot of space and it was hard to fit in the slides here. So it's a large expression, but we can write it explicitly in terms of S only. And so a priori, like, this bound looks quite large, but in most cases we do not need this large bound. We need this only for some cases when L is small. So to be precise, when L is sufficiently large and K is sufficiently large, the bound is order of S to the power 5. And in fact, it is a polynomial of degree 5 in S. And similarly, if L is large but K is small, the bound is a polynomial of degree 10 in S. And finally, if L is small, then the bound is 6s to the power 6s to the power 18s. So it's quite large in the case of small l. And so this result is stronger than the above conjectures, because first of all, like, it deals with the general impermissible part k, and at the same time it produces a bound which depends only on s. And moreover, the bound is explicitly known. Uh, so that was not something that was required in the conjectures. The conjectures only uh, asserted that there exists some bound, and they didn't ask us to find some explicit bounds. So we will talk about this in detail later. So next, we define the fourth conjecture. So Berkovich and Uncu also defined the Q series GL1Q. So for this, they restricted their attention to partitions having bounded gap between largest part and the smallest part. So the largest part and smallest part have difference which is bounded above by L. So they are only talking about such partitions. And among these partitions, they are comparing the number of partitions which have smallest part 1 with those which have smallest part 2 or more. So, and then, so using Q binomial theorem and some other properties, they were able to deduce that GL1 is related to HL1L. So it's the HLSK series with S equals 1 and K equals L. And so we already have some non-negativity properties for this, and using those, they were able to prove that all the coefficients of GL1Q are non-negative. So it's a non-negative series. So we call the series to be non-negative if all of its coefficients are non-negative, and we denote it by this symbol. So they proved that GL1 is non-negative. So this is a quite interesting result, even in the limiting case L goes to infinity, because then the condition L of pi minus S of pi is less than or equal to L becomes redundant, and we are able to conclude that there are more partitions of any number which have of any number n which have smallest part 1 than those which have smallest part 2 or more. So the number of partitions with smallest part 1 are basically more than half of the total partitions. And then, so similar to GL1, they also defined the series GL2 of Q. So here they compared the partitions with smallest part 2 with those having smallest part 3 or more. And then they conjectured that GL2 of Q is again a non-negative series. So all of its coefficients are non-negative, except for a few exceptions in the beginning. So for example, the coefficient of Q cube in GL2Q is -1. So we have to add an extra Q cube to make it a non-negative series. And for L equals 4 and L equals 3, we have some more exceptional terms. So using our techniques for the previous conjectures, we also proved this conjecture. And so our approach for this work is to construct injective maps between the relevant sets of partitions. And to construct these maps, we use some very basic techniques from number theory, such as Frobenius numbers and some applications of division algorithm. So first of all, we use both of these lemmas repeatedly in our maps. So Sylvester proved that for coprime numbers a and b, whenever n is greater than or equal to a minus 1 times b minus 1, then n can be expressed as a non-negative integer combination of a and b. So this quantity is known as the Frobenius number for a and b. So basically we will use this in the sense that, like, if we remove a part of n for some large enough n, then we can compensate for that by adding appropriate parts of a and b. So, and then for the second lemma, we have that whenever n is greater than or equal to s plus 1, then n can be written as a non-negative combination of numbers between s plus 1 and 2s plus 1. So this is an application of the division algorithm, because suppose n, so we have n as a number between s plus 1 and 2s plus 1, then it is clear that it's a combination of these numbers. But then if n is 2s plus 2, then it is just twice of this number. And if it's 2s plus 3, then this is s plus 1 plus s plus 2. And in general, so and so on. So in terms of number theory, we in number theoretic terms, we say this as like the numbers s plus 1, s plus 2 till 2s plus 1 form a complete reduced residue system modulo s plus 1. And again, we use it in the sense that whenever we have a number greater than or equal to s plus 1, we remove a part of that number and we compensate by adding appropriate parts of s plus 1, s plus 2 through 2s plus 1. And so next we briefly describe a sketch of our proof of the first conjecture for L greater than or equal to S plus 3. So that will kind of illustrate our techniques. And so first of all, f of s is defined as 10s minus 2 times 15s minus 3 plus 8s. So this we will see that this is like Arrhenius number of 10s minus 1 and 15s minus 2, because that is a minus 1 times b minus 1. So this is so defined. And then kappa of s is a quantity defined in terms of f of s. And then we prove that whenever n is greater than or equal to kappa of s, then there are more partitions of n in CLS1 than in CLS2. So that is what we wanted to prove. So here we are only including the proof in the case L greater than or equal to S plus 3. The proof for smaller L is quite harder. And so to prove this, we construct an injective map from uh, the second set to the first set. So we want to construct a map, this map phi, and so we take any partition pi of n in CLS2 and we want to map it to a partition in CLS1. So we recall the definitions of CLS2 and CLS1. So in CLS2, all parts lie between s plus 1 and L plus s. So it has this form. And in CLS1, we have smallest part is S, and L plus S minus 1 does not appear as a part. So basically, to map this partition pi in CLS1, we need to remove all the parts of L plus S minus 1. And to compensate, we need to add some parts of S because the smallest part should be S. And we need to ensure that the resultant partition remains a partition of N. So the norm of the resultant partition should be same as the norm of the original partition. And to construct this map, we consider several cases depending on the frequency of L plus S minus 1. And for brevity, we denote this frequency by F. So our strategy for ensuring that the map is injective is to construct the map in such a way that for different cases, the partitions in the image have different frequencies of S. So like in all the different cases, the partitions in the image have different frequencies of S. So for example, suppose we have a partition pi1 in case 2a and partition pi2 in case 2b2, then the image of pi1 has different frequency of S than the image of pi2, because here it is a multiple of 12 and here it is 20. So the images of pi1 and pi2 are different. So there is no, there will be no problem in the injectivity of the map once we ensure that the map is injective within each case. So we have kind of reduced the problem of overall injectivity to local injectivity within the case. And for that, then we construct the map. So we consider the first case when f is greater than or equal to 1. So we basically have some parts of L plus S minus 1, and we need to remove those parts and add some parts of S to compensate. So we remove all the f parts of L plus S minus 1, and to compensate, we add back 2f minus 1 parts of S. So, and then we further need to compensate to add the number, the difference between these numbers, and we can rewrite this difference as follows. So since we are in the case L greater than or equal to S plus 3, so the quantity in the bracket is greater than or equal to 1, and F is also greater than or equal to 1. And so the resultant difference is greater than or equal to S plus 1. And so as remarked before, since any number greater than or equal to S plus 1 can be written as some combination of S plus 1, S plus 2 till 2S plus 1. So we can compensate by adding appropriate parts of S plus 1, S plus 2 through to S plus 1. So to conclude this case, we remove all the F parts of L plus S minus 1, and we compensate by adding 2F minus 1 parts of S, and then we add appropriate parts of S plus 1, S plus 2 till to S plus 1. And then so in the image, so the frequency of S will be 2F minus 1. So the frequency of S basically helps us to recover the value of F, and thus we can construct back the original partition because we can find the value of F. So the map is injective within this case. And we also remark that the image is 2f minus 1 is an odd number. So, but here we are saying we are splitting the case 1 into 2 parts, odd numbers other than 15 and 14. So far, we only have odd numbers. So we do that because we will need 15 later. So once we go through the other steps, we will slightly modify the proof to divide this into the two relevant cases. And then for case 2, we have f equals 0. So this time we don't have any parts of L plus S minus 1 to remove. And we just need to remove the parts from the remaining elements and compensate by adding some relevant parts of S. So for that, we have further subcase 2a, and we suppose that there exists some m less than f of s, which has a large enough frequency. So there is some m less than f of s with at least 12 s parts of m, and we let m naught be the least such number. So then in this case, we remove 12 s parts of m naught, and we compensate by adding 12 m naught parts of s. So we have added back s and balanced so as to retain the norm. And then in this case, from the frequency of s in the image, uh, which is 12 m naught, we can recover the value of m naught, and thus the map is injective within this case. And then in the other case 2b, so we suppose the opposite assumption. So for every m less than f of s, the frequency is less than 12s. So basically, whenever we are on the left of f of s, the frequency is low. So we have low frequency terms. Frequency of each of them is at most 12s minus 1. So then so if all of them have frequency less than or equal to 12s minus 1, that basically means so like in our definition of kappa of s, so kappa of s is 12s minus 1 times this sum plus 1. So that means that kappa of s is large enough. So whenever n greater than or equal to kappa of s is large enough, so that means there must be some parts greater than or equal to f of s which appear in the partition, because n is quite large and all of these are small. So basically kappa of s has been chosen so that there exists an h greater than or equal to f of s such that h appears with a non-zero frequency, and we let L be the least such number. So we can rewrite pi as follows. So L is the number after f of s minus 1, which has a non-zero frequency. And so L is greater than or equal to f of s. So L minus 8s is greater than or equal to f of s minus 8s. But f of s was defined as 8s plus this quantity. So f of s minus 8s is this product. So L minus 8s is greater than or equal to this product, which is nothing but the Frobenius number of 10s minus 1 and 15s minus 2. So this means we can write L minus 8s as a combination of 10s minus 1 and 15s minus 2. So note that to say that we can, this is the Frobenius number of 10s minus 1 and 15s minus 2. We need to make sure that these are co-prime numbers, but that is easy to show because 3 times the first number minus 2 times the second number is 1. So by Bezo's identity, we know that the GCD is 1. And then a natural attempt will be to remove a part of L, and then to compensate, we add back 8 parts of S and XL parts of 10s minus 1 and YL parts of 15s minus 2. But there will be a problem with the injectivity of this map, because this time the frequency of S in the image is 8, which is a fixed number. And so we will not be able to recover the value of L. However, this problem could be overcome if we were given that the frequency of 10s minus 1 and frequency of 15s minus 2 were both 0, because in that case, the map would have looked something like this. And then in the image, so from the frequency of 10s minus 1, we could have recovered the value of XL. And similarly, from the frequency of 15s minus 2 in the image, we could have recovered YL. And then from the defining equation for XL and YL, we could have recovered back the value of L, and the map would have been injective. So the only question is, how can we reasonably justify having two zero frequencies like 10s minus 1 and 15s minus 2, or maybe some other similar terms like that. So for that, we have the following trick. And so suppose 5s plus 1 and 10s minus 1 both appear with non-zero frequencies. So we remove a part of each of them, and to compensate, we add 15 parts of s. So uh, so uh, this completes this part, and for after that we can assume that at least one of them is zero. So, and similarly we can do for 5s plus 2 and 15s minus 2. So if both of them appear with a non-zero frequency, we remove a part of each of them, and to compensate we add back 20 parts of s. And then we can assume that at least one of them is zero. So at least one of these is zero, and at least one of these is zero. So at least two of these four are zero. So either these two are zero, or these two, or the cross ones. So we get four options. So at least one of these statements is true. So like both 10s minus 1 and 15s minus 2 are zero, and similarly the other statements. So first of all, suppose that T1 is true. Then we have f of 10s minus 1 is 0, and f of 15s minus 2 is 0. But that is exactly the kind of assumption that we wanted to make. So that is the scenario that we wanted to be in. So we can recover the values of xl and yl, and we can, from there we can recover L. And but what happens if instead of T1, T2, T3, or T4 are true? So we notice that 10s minus 1 and 15s minus 2 are the largest numbers out of these. And so if L is greater than or equal to f of s, so L minus 8s is greater than or equal to the Frobenius of these two numbers. So it is automatically greater than or equal to the Frobenius of the rest of the numbers. And the same argument carries forward. Instead of these numbers 10s minus 1 and 15s minus 2, we have the same argument for the other numbers. And instead of s to the power 8, we choose some other frequencies of s which had not been taken yet, so 6, 4, and 2. And so if we look back in our table, so we have frequencies 2, 4, 6, 8 coming from this case, and 15 and 20 coming from this case, and multiples of 12 from 2a. Finally, we had odd numbers here and 15 here, so 14 was not taken. So we have to avoid 15. So in this particular case, if we take f equals 8, then we get 2 times f minus 1 is 15. So we get 15 parts of s. So we modify that a bit. So instead of taking 15, we take 14 parts of s. We add 14 parts of s, and then the resultant number is greater than or equal to 2s plus 1. And again, we can compensate by adding appropriate parts. So by making this small modification, we uh, have this as odd numbers other than 15 and 14. And so now 1a and 2b1 do not clash, and all the cases correspond to different frequencies of S. So this completes our proof for the case L greater than or equal to S plus 3 of the first conjecture. And so finally, uh, so in a recent preprint, Zhang and Zhang also gave proofs of the first three conjectures out of the four conjectures. So their proofs are analytic for some cases and combinatorial for some others, whereas our methods are entirely combinatorial. So being analytic, their methods are somewhat more straightforward than ours, but their results are asymptotic because of that and do not give explicit bounds. So being combinatorial, our methods give explicit bounds and also lead to a proof of the fourth conjecture. So like their their results are asymptotic because they crucially use theorem of Frobenius and Schur many times. So this counts the number of partitions of a positive integer n whose parts are restricted to a given set of integers having GCD1. So like this is an asymptotic result, and so it kind of says that as n goes to infinity, this is true. So it is unknown when this is accurate, and even it's unknown when this quantity is uh, non-zero. So that's the well-known Frobenius coin problem. And so because of this, they kind of get that the coefficient of HLSK is positive as n goes to infinity. So they get the existence of a bound after which it becomes positive, but do not get the explicit bounds. So for that, the combinatorial approach helps. And so finally, for the references, we have this paper for which we have an archive preprint, and recently this got accepted in the journal in Annals of Combinatorics. And yeah, so thank you for your attention. If you have any questions, please let me know.
Thank you, Demo. Thank you for the talk.
Thanks.
Let's unmute and clap for Demo. Okay, any question?
Damanvir, hello?
Hi.
Can you go a few slides back?
Yeah.
Um, okay, no, it's fine. I had a question, but actually I can just ask you later.
Okay. Actually, I have a question. So in one slide, you write down some lower bounds of n. Well, the lower bound depends on the relation between L and S. So when L is quite small, then you got, yeah, exactly this page. When L is small, less than 3s plus 2, you get sort of a worse lower bound, right?
Yeah.
So my question is do you expect one can improve this lower bound by using some other technique or methods?
So like,
do you expect this bound is indeed a polynomial in terms of S, not a exponential in S?
so I mean, like, I will be surprised if there's a polynomial bound, but
Okay.
because like this is the best we could get from our technique. So I don't know if the
Okay.
bound can be so much improved.
Oh, okay, I see. Yeah.
but Damanvir,
Yeah.
there's no, you don't really have any notion that there's no reason to believe these bounds are anywhere near optimal, right?
No,
Yeah.
like,
Okay. Okay. Got that. Yeah. All right. If no further question, let's turn to the sharing session.